This is the second video in the 6-3 day 1 set, and we're going to pick up from the sum and difference rules. So we had just done the additivity rule, saying that we could put two intervals together. So we're going to switch functions up. So I'm giving you some given information in the box, telling you what certain integrals are worth. And the sum and difference rule says this. It says if you have two totally different curves, notice how we've got h of x and g of x. If you have two totally different curves and we want to see what happens, but we don't know what happens to them as one combined curve, let's say maybe this was something like x squared plus sine of x. If I know what happens to each of those separately on the interval -2 to 7, I should be able to combine what happens to them from -2 to 7 on each of their graphs separately. So it's saying if you want to know about the sum or difference, polynomials fall under this rule. So think of x squared plus 2x being two separate functions. We can see what happens to the first function on area under the curve, that first integral, and then add or subtract, depending on what the original equation says, what the second one does. So we've got the question of what's the integral from -2 to 7 of the sum of h of x plus g of x, and I don't have that in the given box. But what I do have is what happens from -2 to 7 of just h of x. And again, make sure that that's closed, because again, dx for your differential. And then over that same set of bounds, if I can find out what happened to g of x, then I can go ahead and combine those two and get the original sum or difference of those two to get the intended integral value. So from -2 to 7, h of x is worth 5, the integral. And from -2 to 7, I'm given that g of x is -3. So the integral sum would be 2. Again, you want to be careful with integrals, just like derivatives, that you don't apply rules that you're making up, that you only use rules that you know exist. And remember, derivatives had rules for sums and products and differences and all sorts of things. All right, the max minimum inequality rule makes a lot of sense, but let's not look at how it's written yet. This could be for any curve, and in any curve, there's always a highest and a lowest place in that interval. So I just picked a really smooth curve that's increasing, and these will happen to fall at their endpoints. But I'm going to look between 1 and 4 on this curve, and I'm going to look between 1 and 4 3 different times to get the idea of what we're looking for. The actual integral itself we'd be looking for would be the area between the curve, net sum of the area between the curve and the x-axis. So this would be the actual integral that we'd be looking for. And that area between the curve and the x-axis will always fall between or equal to, so a little bit sandwich theorem-ish, but not that much difficulty, is they said, well, what if we took the minimum value of f that occurred somewhere on that curve from b to a? So between 1 and 4, the minimum value on the curve happens to happen for this curve at the left endpoint. Not always the case. What if we made our minimum value of f times our base and evaluated our integral as an estimate with that area? And they're saying, well, that should always be smaller than or equal to the actual area, the blue in the middle. And if we go to the highest point on that curve, in this case, which happens to be the right endpoint, but not always, and if we made our base b minus a and our height the highest f value that ever occurs on that interval, the area in here should be more than or equal to the actual integral value. So the idea being that my green area from the least value, the minimum height that the function ever displays from a to b, times its base, should be a smaller area or maybe exactly the same as the actual area, our blue area, and that blue area for the actual integral should be smaller than or equal to the area if we took the highest y value times the base. And again, if the function were a constant, all three of these would be the same. If the function had lots of high points and low points, then this might have more meaning, as far as you can see that the green one is obviously less area than the blue, and the blue is obviously less than the red. So wherever the highest and the lowest occur, not necessarily at the endpoints. All right, the dominion rule. Dominion is all about who's higher on a curve, having more area between themselves and the x-axis than whoever's lower on the y-axis. So the green curve that I have here is clearly greater than the blue curve. So my green curve is f of x. My blue curve is g of x. and what is absolutely true for the interval from A to B, and we will make our interval A to B start here and go to here just for the interest of having it defined. The green curve is taller than or has higher y outputs than the blue curve the whole time on that interval A to B. So what they're saying then is the area under the curve from my higher function, and if I do that in my interval, the green amount of area, or integral value I should say, is always going to be a bigger number than the blue one. Oops, totally went off my curve, but you get the idea. Now this makes people nervous because they think like the integral from the higher curve, that would only work above the x-axis. So one way to kind of rephrase it, the interval from the higher curve integral has to be greater than, or maybe it's exactly equal to, it depends, the integral from the lower curve. But this makes people nervous about, yeah, except if they're under the x-axis, I bet that flips. So let's actually take a look at one for a second, and let's make them below the x-axis, and let's talk about who's the higher curve and the lower curve, and I'm just going to make them triangles for the sake of argument. So my g of x, and then I'm going to make a curve above that, my f of x. And if I'm going on that interval from a to b, so I'm going to make a here and b right here, what people say is, well, f of x is above g of x, but g of x has more area. That's true, but that's not what this is saying. So if I did the integral from my blue curve, my higher curve, let's say that came up -10, making up these numbers. My integral for that same interval for my green curve might be something like -20. Well, -10 is bigger than -20, so it's still true. So therefore, this is a rule that holds no matter where the curves are, the higher curve's integral value is higher than the lower curve's integral value. All right, so for all of these, I gave you some information about some integrals, and we're going to see if it's possible to use this information to come up with a value for some integrals. So I'd suggest you pause the video right now and try a few of them to truly test yourself and see if you get what's going on, and then come back and I'll go through all of them. So pause now, try it yourself first, then come back. If you're back, a couple things to think about. This first one should be 2. And we can get it because we can switch the bounds here. They're going from 4 to 1, but we happen to have in this second one right here, one whose bounds are opposite, so therefore we have that order of integration idea that we can get this one by taking the opposite, switch the bounds to one whose integral value we know, and therefore we can take the opposite of the one we know. So the opposite of -2, we get +2. The next one down, we can't tell from the information, so cannot determine. Just because we don't have the correct information here doesn't mean that that's always the case. From -2 to 2 for h of x, I have no information about h of x from -2 to -1, and I have no information about it from 1 until 2. So I can't determine for h of x what the rest of that graph might do, and therefore what might happen to that integral value. Same for 0 to 1 of f of x. I can't tell. And the reason is when you look at what we know about f of x, we know what happens from -1 to 1, but we don't know if that's an equal amount of area from -1 to 0 and from 0 to 1. And therefore, without knowing more about the curve, we have no property that lets us do anything proportionally, because again, we don't know about what the shape of the curve is. All right, this next one down should be 3, and you can do that in parts. We know what happens to f of x from -1 to 1, and then picking up from 1 to 4. So we can do a little additivity there to get that one. Okay, 5 and -2 go together. These last few, we can't determine. The reason we can't determine this last one is I don't know what happens to h of x from -1 until 4. I don't have that information. If I knew, I could get the sum of the two, because I do know what happens to f of x from -1 to 1 and from 1 to 4, but we don't have information in order to get that for these bounds. We don't have from -1 to 4 any information about h of x, so I can't do that one. And finally, this last one should come up 31. We're going to have to do a little constant multipliers. In other words, I know what happens from f of x from -1 to 1, so that constant multiplier says I can double it. I know what happens from h of x from -1 to 1, so I can triple that and put that together. So it's going to be twice the 5 that I knew about and 3 times the 7 that I knew about.